So welcome to the 10th lecture, and we had gone back to the second module of the course. Last day the 10th, yeah? Right. So you can see what we were doing in the recording also.
रिकॉर्डिंग में आवाज सही नहीं आ रही है।
हाँ वो लगा लें, हेडफोन लगा लें फिलहाल गुजारा कर लें. So what we had been looking at in the last lecture was some common distributions that often show up in probability theory, right? So the function fx that we looked at, now we were looking at, okay, what are the common values of this function or common shapes of this function, right? So like in normal mathematics you say nonlinear functions, but then you have special instances of nonlinear functions, right? There is कोई nonlinear function बता सकते हैं आप? Quadratic. That's a special case, right? If I say fx is nonlinear, I'm not saying which one it is. Yeah, I'm just explaining that it has some property that is not linear. But then, what are the common instances of a nonlinear function? Well, x squared, the exponential, e to power x, cosine, sine, log x, right? So then you study several common types of nonlinear functions. Similarly, so far we have talked about distribution functions. Fx, what properties they have, what do they mean, how to calculate, but what are the common functions that are there? And we split that problem into two parts, just like before: continuous random variables and discrete random variables. And in the last lecture I covered four important common distributions for the discrete case. Okay, and those were uniform distribution, the binomial, geometric, and negative binomial. Yeah? And today we will do the fourth one, which is Poisson distribution, and with that we are mostly done with the discrete case, and then we will go to the continuous case. Yeah, and in the continuous case we will look at uniform again for the continuous case, the Gaussian distribution or the normal distribution, and exponential distribution. So this is the main plan, and it's already in motion. We started working on it last week in the last lecture, and basically we covered. So what we had been talking about was general PDFs or distribution functions, what properties they have. This is written for the discrete case. Then we said, okay, what are the common functions that are usually showing up? Like in nonlinear, it's logarithmic, cosine, sine, sinusoid, exponential, like that. So it seems, now there are many, but for a first course, I think if you are well familiar with these five, you have got a very good start. Okay, so we covered up to here in great detail last time. Now I want to start with the Poisson distribution. All of these were covered for the case where x is discrete random variable. And after we are done with Poisson, the last one for discrete today, we will also shift to the continuous case where x will now be continuous. Yeah. So coming to Poisson distribution, what is it? Where does it show up? Just the common distributions often show up in situations, in realistic situations of probability. Like uniform, if you are unsure or if everything is equally likely, like rolling a die. By nature, we know unless there is some cheating going on, all the events are equally likely. Yes? So, somebody being picked up randomly, everybody is equally likely. So, the uniform distribution comes where you have events being equally likely. So for the case of rolling a dice, all 6 options have equal probability, so we call it uniform. And we covered it in detail last time. Binomial geometric negative often show up in Bernoulli trials. Bernoulli trials is just a fancy name given to probabilistic experiments or works. Let's say you buy 10 microchips. Yes, what is the likelihood that 3 of them will work, for example? This kind of question. Or if you are picking microchips from a box, what is the likelihood that the third one will be the first to work, the first 2 will fail? Yes. Or what is the likelihood that you will have to pick 10 microchips for exactly 3 of them to work? Now, these are the kind of questions that they may look like, well, they're made up. They're not as simple as rolling a die. They show up in many problems of planning. If you're a manager, if you're going to plan a supply chain, for example, those kind of questions show up very often. And they lead to a set of distributions, this binomial geometric, negative binomial, and many more. But these are the most common ones, and we covered those in details. Now we ask or look at a different kind of situation which will lead to yet another class. Look, exponential, sinusoidal, logarithmic, nonlinear functions, but different situations lead to them, right? Sinusoidal कहाँ आते हैं physics में? AC? Yeah, you mean this one? Yeah, okay. AC curve, or wherever you have some sort of oscillatory motion. Yes, or oscillations in those waves that are there. So just like that, here also in probability theory, these functions show up in different scenarios. Yeah. Now the third scenario, the third group of scenarios that we want to see, these are in one group, second group, and the third one is based on Poisson distribution, and that is that a lot of work that we do or the things we work with where probability is involved has something to do with counting. Okay, what do we mean by that? Well, you could be counting, for example. So we did this, all of these, sorry, it's all done last time. I'll just skip through this. Yes. Yeah. Here we are, counting process. For example, how many customers visit a shop in a given time duration? Now, this is a very important question. For whom? For example, the owner, the manager. Too many customers, 10 customers visiting per hour. Do you need one shopkeeper there, one clerk there, or 2? Right? At night, how many visiting per hour? So, it's a very natural question. It helps if you can answer this smartly using probability theory. You can plan well and your customers will be happy without you having to pay 3 clerks. एक हाल तो ये है ना कि आप maximum number वहाँ बिठा दें. Then what's the loss? You have to pay them, right? So planning, decision making, all those, this kind of questions, counting questions, often lead to counting distributions. Among them is the Poisson distribution, the most important in this group. How many students fall asleep during my lecture? Not very useful, I guess, but how many people visit a given website? Yes? Yeah? So you can have expected earning from your channel. How does YouTube know what to expect? Yeah, what is your expected earning, for example? So, how many calls you get during the lecture? Okay, that's how many drops of rain fall in a given area, right? So, what's this for? Agriculture, for example. Yes. So, all of these questions are related to counting. Yes, and there is randomness in them mostly. So what happens when you're doing the counting? Let's define a certain set of counting. Now, whenever you would know that whenever you make something formal, whenever you bring it into mathematics, you have to define a set of assumptions or limitations. Yeah, पूरा generic कुछ नहीं होता, बहुत मुश्किल होता है. So always you have to, then where do you bring those assumptions from? If you make them so unrealistic कि वो कभी काम ही ना आए, फायदा नहीं है ना. So usually you bring those assumptions from experience, from your use, from your requirements. Yeah. So there are some assumptions that we're going to put here. First, we're going to define a counting process. So let X be the number of some specific random events that occur in duration, say T. Yeah. Now T, we say duration and T, but it doesn't have to be. It can be length also. You bought a rod and number of defects per inch, for example. Yeah. So we will say duration, time, but we're not just restricted to time. Any measurement and any interval is that measurement. Yeah. So for example, if T is 2 hours, then X could be number of calls you get in 2 hours. Yeah. Now assume that the counting begins with 0. We have to start somewhere. So your counting, let's say, begins with 0. So X is 0 for T equals 0. So your random variable starts at 0. Yeah. And at T equals 0. Then you could ask me, okay, number of calls in this 1 hour, or the number of calls in these 2 hours, or the number of calls in these 3 hours. Each of those is a random variable. Yeah. Okay. So these we call intervals. Different kind of intervals. You could define them the way you like. Now let X be the number of sums. This we have already said. These are the assumptions that I was talking about. To make things formal, we have to bring in some assumptions, and those assumptions are usually taken from experience or requirement, and they have to be those assumptions that are usually satisfied. Otherwise, the file nahi hoi development. Yeah. So the number of events in two non-overlapping intervals are independent. Okay. What does that mean? That means that the number of calls I receive in this interval is independent of the number of calls I receive in this, because they are non-overlapping. But these two are overlapping, so they can be dependent. Independence ka concept pada na? Yeah. So as long as any two intervals are independent, are non-overlapping, then the number of events happening in them are we're not saying it's true always. We're saying that is the assumption we will start with. Yeah. It's a very common and useful assumption, and this is the first course. This assumption also makes the problem easier. We have distributions where overlapping, non-overlapping intervals can have dependent numbers, but then the distribution becomes harder. Second course aayega, right? So let's start somewhere. So we start here. The first assumption: the number of events in two non-overlapping intervals are independent. Okay. Second, the number of events during an interval depend only on the length of the interval, nothing else. Okay. So if an interval is long, yeah, or short, the number of events or number of calls will increase or decrease accordingly. Okay, but nothing else. Okay. That's our second assumption. Third assumption: by nothing else we mean also that we're saying it doesn't matter when the interval occurs. Yeah. So the probability of two events occurring at the same time is 0. Okay. Again, some of these assumptions are simplifying. दो customer इकट्ठे आ सकते हैं अंदर, right? So does that mean that Poisson distribution will not work? Actually, we have generalizations which then ease these conditions later. पर अगर हम उससे शुरू करेंगे ना, वो जो formula बनेगा, वो इस वक्त आपको समझ नहीं आएगा. We have to start in assumptions which can get things started and still are useful. The average number of events per unit interval is a constant. Okay, so the average number of events That means the number of events divided by the size of the interval is constant. Okay, so that is of course saying that if the interval becomes large, then the number of events also increases proportionally. तभी उसका ratio constant आएगी lambda. So it's very common to use the symbol lambda here. Now कितनी है ये 1 2 3 4 4 assumptions. Yes, counting process, there is a counting process. The fifth assumption ये है, counting begins at 0 for our convenience. You could start somewhere else, but थोड़ा सा और cramped है. Okay, so now if these assumptions are met in a counting process, then it can be shown that the distribution of x follows the following formula called Poisson distribution. Okay, x key, what is the formula that x will follow? Remember x was what? So in this case, x is the number of events, number of calls you receive, number of customers entering your shop, number of people clicking your website, yes, in a given time. What time? The time interval is here, t. The arrival rate, which is supposed to be fixed, is lambda here, and x tells you what is the probability that if you put 5 here, you know what you're asking? If you put 5 here and if you put t equal to 1, let's say second, or 1 hour, let's say for customers. So if you put 5 in small x and 1 hour in t, you're asking what is the probability that in 1 hour I will get 5 customers. Okay, and if the assumptions, the previous assumptions are agreed upon, are met, then you can answer that question from here. Okay, what is the probability that in 5 hours I will get 5 customers? What is the probability that in 10 hours, put 10 here, okay, and lambda has to be written accordingly. Whatever units you are using here, hour, minute, second, वही lambda में भी होनी चाहिए. Right? Not के rate is in seconds and time is given in hours. Okay, so that's from basic physics and math. You know that. That's why per unit time. So t, whatever question you want to ask is here. That is why, see the values of x. What are the possible values of x? 0, 1, 2. Why is that? As we said, we're counting number of events. Right? So minus 3 events तो नहीं हो सकती. 0 होगी, 1 होगी, 2 होगी, 3 होगी. So you are allowed to use this formula only for, because that's how we developed it. It's a counting process. Now we are not proving this formula. When assumptions say how you get here, I do that in a graduate course, right? It's actually a limiting case of the binomial distribution that we did last time, but not here. Up with results. So for you, even if you understand the assumptions, the idea of a counting process, I will be happy with that. Yeah, and of course how to use the formula. This one. Right. So yeah, E is, as you know, whatever E is. So it's E minus lambda t x over x factorial. Yeah. What does it say? If you put x 0 here, t 1 hour, you are saying what's the probability that no customer will come in 1 hour. Right? So you can calculate different probabilities for 0, 1, 2, 3, 4, and so on. So now I like to mention this that as I said, Poisson shows up, or the counting processes are very common, right? We often have to count situations. But among the counting processes, by the way, counting processes is a large class. Okay, so pointer something. Yeah. So counting processes are a large class. Counting. Among them is the subclass which satisfies the assumptions that we just saw, and they follow the Poisson distribution. What do we mean by they follow the Poisson distribution? That formula. Yeah, e2 minus x lambda t x over x factorial. Yeah, so we call them the Poisson process. But intuitively, when do real problems lead to Poisson distribution? And for that we have the law of rare events. Okay, the law of rare events says that whenever you have a situation where a large number of events can occur, but only a few actually do in a given time, then you are dealing with relatively rare events. Okay, I'll explain it. But let me complete this by saying that when you are dealing with rare events, normally or often their distribution is Poisson distribution. This is more of an intuitive understanding. How many people can call my mobile number in the next 1 minute? Do you know? कितने लोग कॉल कर सकते हैं? कोई अंदाजा है? I'm not saying how many will call. I'm saying how many can call.
जिनके पास नंबर है
जिनके पास
नंबर है
नहीं भी हो, रैंडम कॉल भी कर सकते हैं. कितने हो गए? दुनिया में anybody who has a phone and enough money to make an international call, right? अभी लिंक कर सकते हैं ना? Billions में है बात, right? How many will actually call me next 1 hour? Maybe 0, maybe 1, right? Since I'm the D, so एक तो आ जाती है. अगर ना होता तो शायद 0, right? कैसे ही आ जाती है इतनी देर में. But so isn't that a rare event? Given के billions could call me now, right? Or in the next hour, billions could call me, but only a few actually do. So that is the law of rare events. It talks about situations where a lot of events could occur, but only a very small subset occurs at a time. Okay? And such situations often lead to the Poisson distribution. This is another way of looking at the counting process. If you are going to count those events per unit time, yeah, then you will most often be dealing with Poisson distribution. So, yeah, I explained that. So, discrete random variables that represent how many of these independent rare events actually occur in a given interval are often, I write often because they are generalizations in other cases, best represented by Poisson distribution, which we have already discussed. And lambda is the number of events per unit time. Sometimes we call it intensity. Why? Because if lambda is high, number of arrivals in a unit time is high. So you are dealing with a high intensity situation. Yes, आपकी दुकान में ज़्यादा लोग आते हैं. जिनका lambda high है, जिनका कम है, वो कारोबार थोड़ा not very good था. So how does Poisson distribution look? Well, Poisson distribution for different lambdas. Remember what is lambda? Number of events per unit time. We also call it intensity. Yeah. So firstly, Poisson is a discrete distribution. Yeah. Continuous नहीं है. So this line is misleading. ये सिर्फ आपको दिखाने के लिए बनाई गई है. Okay. So basically it's these dots, because remember Poisson distribution is defined for 0, 1, 2, 3, 4, 5. For other values it's 0. So वो आपको बार सिर्फ याद है. You can draw lines, but then you don't get a feel for the shape. So उन्होंने line बना दी है. Sometimes we do that, but it's these dots that actually represent the Poisson distribution. So notice the way the Poisson distribution usually is that it peaks at lambda. Lambda 10 है ना? Yeah. So its peak is at usually at lambda, and then fewer than or below lambda the probability decreases, and above lambda, so the probability in this case, the probability that there will be 10 customers in a unit time is the highest, which is corresponding to your expected or the lambda value here, the intensity. Whereas the probability that you will get, let's say, 7 customers per unit time is dropped. Probability that you will get 13 customers is lower. So it's maximum near the expected or the intensity lambda, and then it drops off, right? So it's very unlikely if your intensity is 10. On average or mostly you are getting 10 customers per hour. Then what's the probability that you will get 1 customer in the next hour? There is a probability, but it should be low. Makes sense or no? Because you are saying your intensity is 10. Compared to someone whose intensity is 4, that means they are expecting 4 customers per hour. Now what's their probability that they will get 1 customer in the next hour? That has to be higher than these guys. Yes? So it makes perfect sense. This function, these values come from this function. आप इस function में कर लेंगे, but it also makes perfect sense here. इसमें काफी जो symmetry है, as you go away from the expected or the intensity, this thing, your probability of that happening decreases, but that can still happen, right? Remember, we are dealing with probability theory, deterministic नहीं है. Even the best shop on the market could have a bad hour when nobody shows up. हो सकता है, right? पर क्या है? If you're, अगर आप expect ही let's say आप expect ही 1 customer करते हैं per hour, so it is very highly likely that there will be no one coming. Yeah, but if you expect 4 or usually you have 4 customers per hour, then 0 is less likely. And if you expect or usually have 10 customers per hour, 0 is even more less likely. Yeah, so it's going this way with lambda increasing, and the probabilities of the extreme cases is also dropping off really fast. Okay, so yeah, okay, so this is for a continuous case. Yeah, so any questions so far before I go to the continuous case? So we will repeat this, what we did for discrete, we will do now for continuous, but there we have their own set of distribution. Yes?
Lambda mean कोई similarity?
Mean lambda is the Poisson distribution. Let me see, I think that is in this case that is the mean, if I recall correctly. I don't have it here. I think the Poisson distribution's mean is the lambda, but here we are just defining it as a parameter that represents the number of arrivals per unit time. Yeah, mean is a very special function. क्या है वो? ex, x, fx. Yeah, integral or summation. If you do that for this distribution, how would you do it? So to find the actual mean, you will have to write this function, multiply by x and sum over all values of x, which are 0, 1, 2, 3 up to infinity. Yes? So वो एक series बन जाएगी. You'll have to sum that series, and if that leads to lambda, then the mean is lambda. Right? So otherwise उस तरह नहीं है. It's not exactly like that. Yeah, I should have written the mean and variance of Poisson here. I forgot, I think. So anyway, you can check your book. Yeah, I think it is lambda. Okay. So now we go to the continuous case. Yeah. Okay. So that we go here. Start. So the first distribution we did for the discrete case was uniform distribution. Yes, uniform distribution, that is all events are equally likely. So that is also the easiest case in continuous random variables. Okay. So for the case of a continuous random variable, we will be so if x is a continuous random variable, we plan to talk about three distributions. X, it has distribution fx, and we will talk about three common functions that represent fx for the continuous case. One of them will be the uniform distribution. The other, arguably the most important distribution in probability theory, the Gaussian, normal, दो नाम है इसके, we use them interchangeably. So I write the other name normal distribution or Gaussian distribution, and the third one, actually we will probably see this, then will come here, exponential. Now, by far these are not the only ones, there's बहुत ज़्यादा distribution है, again, but we stick to the most common and the most important ones for a first course. We will see some others later, chi-squared, t distribution. Briefly, we will see them when we go to the next module. But for now, I want to focus on this. If you get the concept, then the other distributions are just other functions. So, uniform distribution. Okay. So, if you consider a random variable between 2 points A and B, and the likelihood of that random variable taking, so let's say I have a continuous random variable that exists between A and B. By exist, I mean that the probability that it's below A and above B is 0. Then, if I now tell you that x takes a value between A and B with equal probability or equal likelihood, इनमें से कोई भी value उसने लेनी है with equal likelihood, no particular value in here in this continuous line from A to B is more likely or less likely than the other. तो फिर उसका function कैसे बनेगा? जो fx का straight line also. That is where the word uniform, no ridges and peaks and dips, uniform. So we saw the uniform for the discrete case. Rolling a die is a uniform, leads to a uniform distribution, 1 by 6, 1 by 6, 1, So for the continuous case, it's a continuous random variable that takes values with equal likelihood in some range. This represents that they all are equally likely. कहीं भी ऊपर नहीं जाती, कहीं भी नीचे जाती, तो no one is less likely, no one is more likely. They are all equally likely. Okay, so let's call this level k. Now, can somebody tell me what should be the value of k? क्या होगा? So this height I'm talking about, right? So it's uniform between A and B. This is your fx. So k is what? A and B. Really? This is one value. What's the level? A, so x has, these are the values of x, right? A and B. And also what the value of fx should be, k should be 1. Any other thoughts? ये तो ये कह रहे हैं कि they are equally likely. It's not saying it could be 10 equally likely, but which one is allowed? 0.5. Okay, that's specific. Any other? What's the thought process? What is the requirement on fx? कोई requirements याद है उसकी properties?
0 or 1 kilo.
Yeah, it cannot be negative. And what else? Both the probabilities are between 0 and 1. So total area under fx should be 1. यही था ना? होना चाहिए ना? So the total area under fx, if it is the continuous case, should always be 1. If it is less than 1 or more than 1, this is not a valid PDF. किया था ना हमने? For discrete case, it was replaced by summation fx should be 1. So, what's the total area under fx? क्या है? वो तो 1 तो होना चाहिए, अभी फंक्शन रहता है. What's the area under? This is the area. क्या है फंक्शन रिक्वायर्ड?
b minus a into
b minus a into
k.
rectangle है ना? Should be. Yeah, this comes from our knowledge of distribution functions. Yes. So what is k then?
1 over b minus
Yes. So 0 या 1.5 नहीं, general answer नहीं है इसका. Yeah. So what does that mean? As b goes right, more right, this drops. नीचे जाएगा ना, पतला होता जाएगा rectangle. Yeah. So because we want the total area to be 1. Yeah. So k has to be 1 over b minus a. Yeah. Okay. So basically that is the uniform distribution, and this is how we write it. The random variable that is uniformly distributed fx has probability 1 over this function 1 over b minus a. Okay, we are assuming b greater than a, of course. Yeah. So 1 over b minus a in what range? As long as x is between a and b. So we can write this thing applies to x greater than a, less than b. Yeah. As long as x falls here, it's a constant. That constant we already found has to be 1 over b minus a and 0 otherwise. This distribution is called continuous uniform distribution. क्योंकि एक discrete uniform भी होती है. Yeah. Okay. What is the mean of this distribution? कोई जल्दी से बता सकता है? Mu x. What is it? Definition तो हमें पता है, but if you can interpret, what's the mean? B minus a. Anything else? Mean was what? Center of mass, expected worth. We did all that. Yeah. You have to put a wedge here somewhere, so that the
divided by.
So, if you put the wedge on the left, क्या होगा? To fall to the right. Yeah. दोनों के end middle में नहीं रखना पड़ेगा. Then it will balance. Center of mass, याद? Formula से भी निकल आएगा, but it's fun to do it like that. So ये point क्या है फिर middle?
b minus a by 2. b minus a whole divided. नहीं
ये point चाहिए हमें. आप उसकी length बता रहे हैं. वो आप सही बता रहे हैं कि उसकी length क्या है. लेकिन ये point खुद कहाँ है?
a plus
b over 2. Average. Right? ये तो आप कहते हैं. So it's a plus b over 2. That is this exact point. Yeah. b minus a by 2 ना, वो आपको सिर्फ ये फासला होता है. But you are also here. वो भी ऐड करना उसको. फिर याद है. So its mean is this. Variance you can calculate using the formula, and it turns out to be just like for the discrete case we did that last time. It's going to be b minus a square divided by 12. It's very funny that a number such as 12 shows up in a general case, but it does. Yeah. So the variance and mean. Okay. The variance you calculate using the what? कैसे calculate होती है ये? You will do this. It will be minus infinity to infinity x square minus mean of x, x minus mean of x square fx dx. Yes, इसको solve करना है. Now you know that it's from a to b, so change those limits. You know during a to b it is 1 over b minus a. Put that here. Now you know that its mean is, you just told me, a plus b over 2. Put that here. सिर्फ x रह गया. जस्ट इंटीग्रेट इट आउट, बताइए जवाब आएगा। अगर आप इंटीग्रेशन ठीक कर लें, yeah, so that is the mean and variance of the uniform distribution. Now let's go, this is very easy case, the uniform distribution. Now let's go to the second case. Now where did we get the uniform distribution? You had this continuous random variable over a range which took for values over that range with equal probability. Yeah. Now imagine a situation where you have a continuous random variable which is not negative firstly. Okay. So it's limited to 0 or positive values, and its probability or its relative likelihood of taking higher values drops exponentially. Okay. So just now you saw, let's say, for now you saw that there was something, अगर A 0 है, A to B, you saw uniform. Yes. What if there is a random variable that is non-negative? Okay, that's one condition. Of course, if you allow negative, you will get another distribution. वो थोड़ी सी complicated हो जाएगी. We are restricting ourselves to some specific distribution. For that, we're saying it's non-negative. यहाँ ऐसी कोई requirement नहीं थी. Any A, B, you could be on the left, right, middle, either way then. Here, let's say it's never negative, and its chances of taking higher values drop exponentially. So what is the likelihood that it takes values in here to the left, small values, very high. What is the likelihood that it takes larger values, drops exponentially, keeps dropping exponentially. So how would it look? Of course, it would look like an exponential decay, right? And we do come across such situations where smaller values are very highly likely, whereas the larger values are very rare. They are very less, like exponentially drop. Yeah. So the likelihood of the random variable taking large values drops exponentially. अगर ये दो conditions meet हो रही हो, that it is never negative and its likelihood of taking large values is dropping exponentially, then we call that distribution exponential distribution. Yeah, and often we have this, again we use a parameter lambda, which in this case represents rate of decay. For Poisson, it represented the intensity, average or the number of arrivals per unit time, not really average. Here is the rate of decay. So this drop rate is this lambda, let's say this way, and some books and your textbook also represents it as 1 over beta to maybe distinguish it from Poisson. But anyway, so now if there is a random variable x that has higher decay rate than the other, let's say there is lambda 1 less than lambda 2 less than lambda 3. So what is lambda? There is a lambda 2. There is another random variable that also follows exponential distribution, meaning its likelihood of taking higher value drops, but much faster. Yeah. Then how would it look? Well, that guy. Let's see. Yes. Basically, it's easy to see that that guy would start off here and go down much faster. This is lambda 2. What about lambda 3? Same thing, even more fast. It will never touch, yeah, as I'm totally approaching. So excuse my drawing here. It just goes on, but drops much faster because this one has the highest decay rate. So the decay rate can vary, but all three are following exponential drop. Yes, drop में decay rate फर्क है, otherwise the function is the same, exponential drop. This kind of distributions we write as, let's clear some space for ourselves. We write them as fx equals 1 over beta e minus x over beta for x greater or equal to 0 and 0 for x less than 0. Some books write it as lambda e minus lambda x. Okay, your textbook has a beta, so I just changed it. Just remember, it's just the inverse of the decay rate. Okay, so 1 over beta e minus x over beta. This thing, if you draw it, it shows exponential decay. And this kind of distribution, we call it exponential distribution. How many parameters does this distribution have? 1 beta. Parameter to 8 here. You can only play with that to change. Yeah. How many parameters did the uniform distribution have? 2. A and B. Yeah. So it's important to also keep in mind how many parameters mean what can you play with to change the shape of the distribution without actually changing the function. Uniform is uniform even if A is 1 and B is 10 or B is 100. It's still uniform, right? So you stay within that function, but you change its parameters. That's what the problem. Similarly here, these are all exponential, but then you can play with lambda, which is 1 over beta. So basically you can play with beta here. Yeah. Now it can be shown, I won't derive it here, that the mean of a exponentially distributed random variable is beta. Okay, you can apply the formulas of finding the mean, and you'll find that it is beta, and the variance is beta square. Okay. Now this thing is not so easy to find using the center of mass idea. You go theoretically approach कर रहा है, यहाँ it doesn't work. Okay, fine. Intuition doesn't always work there, yeah, or very simple conceptual approach doesn't always work. Then you go back to rigor. You just apply the formula. What is that? Integral x fx. What will you put in fx for the exponential case? This thing. What will be the limit you will put? 0 to infinity. Why? Because it cannot be negative. Yeah. So you will put 0 to infinity. You will put this fx here, and when you solve this integral, you will get beta. So you will conclude that the mean of a exponential distributed random variable with parameter beta is actually beta itself. Yeah, and for variance, you will actually find beta square. Okay. Now, the exponential distribution has a relation to the Gaussian, to the Poisson distribution. Okay, in Poisson distribution, it will be shown that the, remember what were we doing in Poisson distribution? We were counting the number of events. Yes, but what if we were interested in finding the time duration between two events? That's also a random variable. The time duration between first customer and the second customer and the third customer. कस्टमर प्लान करके तो नहीं आ रहे कि हमने 2-2 मिनट बाद जाना है, राइट? कभी ज़्यादा होगा गैप, कभी कम होगा. In Poisson distribution, we didn't look at that. We just said we're gonna count how many came. Yeah. But if you were interested in saying, okay, how is this? This duration, sometimes very quickly, some customers coming, sometimes very big duration. That duration also is a random variable. It can be shown that duration is actually exponential distributed. Okay, so it can be proven. I won't do it here, but there is a relation between Poisson, which is counting, discrete, and the time intervals which are continuous. So if the process is Poisson, its time intervals are actually, the length of the intervals are actually exponentially distributed. It is continuous. Okay, now to the most important distribution of this field, named after the genius Gauss. So it has two names, Gaussian or normal distribution. And just like for Poisson, we saw for the Poisson we saw the law of rare events. Yes. Here we will see another law, which is we won't see that law, but we'll see a result or related to that. That law is law of large numbers, and to that is related a theorem called the central limit theorem. Yeah. So that will connect the Gaussian distribution to other distributions. So let's see what these are. Now, firstly, आपको Gaussian distribution पता है, normal distribution, bell curve. Yes. Now, it is the most common naturally occurring distribution. Heights of people tend to be, most people, average height. Very short, कम chances. Very tall, कम chances. Yeah. Weights of people, durations, a lot of things are naturally distributed like a bell curve. Yeah. And that bell curve is the normal distribution we're going to talk about. So firstly, there is some physical understanding here that, or let's say practical understanding that many situations are like that. Yeah. Now, another thing is that many phenomena that we study, like for example, if you are studying the temperature of an IC, that temperature or the noise in the IC, you're recording a noise, you're finding that your IC is giving some noise. In most cases, a lot of what you observe in the macro world is based on small randomnesses going on in the micro world. Yeah? What you're looking at is their combined effect, their overall effect, their average effect. Yeah? Now the central limit theorem says that in the general case, it says that almost whatever the distributions of those micro effects, if you look at their macro effect, it will have Gaussian distribution. It's a very powerful theorem. Okay, so let's see that happening in some cases. But I will come back to that also. Let's do an example and see. Let's say you toss a coin. Yeah, just to bring home this point. Coin tossing game where you win 1 rupee for a head and you lose 1 rupee for a tail. Is it a discrete random variable case or a continuous case? Discrete case. Yeah, 3 options. Yeah. Okay. So let's say we say that x is the overall amount you win or lose. Yeah. So x is a random variable. What are its possible values for a single toss? -1 and 1. या आप रुपया lose करेंगे या gain करेंगे. So let's see. -1 and 1. Does it have a uniform distribution? Yes. Discrete uniform distribution. What is the chances of winning, losing 1 rupee? 1 by 2. What are the chances of winning 1 rupee? 1 by 2. Both same levels, so it's a discrete uniform distribution. Equally likely. Yeah, all possibilities are equally likely. Okay. How much do you or what are the different likelihoods of winning different amounts if we do the toss 2 times? कितने रुपए आप जीत या हार सकते हैं? 2 रुपए जीत सकते हैं, 2 हार भी सकते हैं, और क्या हो सकता है?
एक जीत सकते हैं, एक हार सकते हैं।
तो फिर कितना देगा? So the combined effect of 2 tosses, yeah, would be for 1 toss it was clear -1 1. If 2 tosses, 3 possibilities. You win both, you lose both, or 1 win 1 draw. If you win both, you get 2 rupees. If you lose both, you lose 2 rupees. If you win 1, you lose 1, you get nothing. So 3 values are given. So instead of 2 values, now you are dealing with 3 values. Yes. What are the 3 values? 0, -2, and 2. So this was the value of x. X is rupees won. Yeah, when it's positive, you actually win. When it's negative, you lose. Yeah, X is a random variable showing rupees 1. One toss here. What did you look at the combined effect of two tosses? Yeah, how should it look? What is the probability of you winning 2 rupees? Yeah, here it is, but what is it? क्या है?
The probability 1 by 2.
Of winning 2 rupees? 50% chance है. बड़े आप lucky है. 1 over 4 ले. और कोई आंसर? सवाल समझ आ गया. 3 tosses हुए हैं, 3 possibilities -2, 0 और 2. Yeah. So, what is the probability? What is the probability of not winning or
1 by 4 होगा.
This is 1 by 4. Yes. ये 1 by 4 है. अब आप खुद ही सोच लें क्यों है. क्योंकि ये 1 by 2 है. ये क्यों है ये भी आप सोच लें. तो ये क्या है ये भी 1 by 4 है. Why? Again, if you are confused, always go back to the basics. 2 toss हुए, क्या possibilities है? Head head, head tail, tail head, tail tail. Yes, all equally likely. कोई आपको dependence तो नहीं है. This is rupees 2 winning. 1 out of 4 options. 1 out of 4 equally likely options. ये दो तरह से 0 आता है. Yeah, first head, second tail, or first tail, second head. Both ways you win nothing, you lose nothing. That is half. 2 out of 4 equally likely. And then, if you're extremely unlucky, both tails. So it takes this shape. Yeah. Now tell me, if we look at the combined effect of 4 tosses. 4 tosses में क्या होगा? कितने रुपए आप जीत सकते हैं मैक्सिमम? 4 रुपए जीत सकते हैं. लूज कितने करते हैं? 4. कैलकुलेट जा रहा है. So notice what's happening now. So 0 minus 4. What about minus 2 rupees? Possible है ना? थोड़ा सा अगर आप सोचेंगे possible है -2. What about winning 2 rupees? Yes, possible. What about losing 2 rupees? Yes, possible. I won't do it, but if you try different ways, even write out the 4 tosses, you will get these values. 1 over 16 minus 4 की 1 over 16 1 over 16 1 over 4 1 over 4 and 6 over 16, or you could say 3 over 8. Yeah. Now if I draw this out, ये तो वो 0 की line है. This starts with a uniform distribution. Yeah. Each toss itself has a what? Each single toss has what? Uniform distribution. On the micro level, there is nothing Gaussian or bell-shaped there. Yeah. But now, if you start combining their effect, दो tosses का effect already थोड़ी देखें shape लेना शुरू हो रहा है. Bell की 4 tosses पे देखें. ये तो almost अभी से बेल बनता जा रहा है. अब 16 टॉसेस पे क्या होगा? 50 टॉसेस पे बिल्कुल बेल शेप बन जाएगा. Right? It will actually come here. And this is the central limit theorem in action. The central limit theorem says it has variants, there are restrictions. I don't want to bog down with that. In effect, the concept is it's proven mathematically also. And that's where the formula of this bell curve comes in. We will see that formula. Yeah, it says that the underlying effects, firstly, if they are all of them are identical distributed, then they will definitely lead to a bell curve. But if they are not, even then they will lead to a bell curve like this. So the combined effect of many small random events, variables, when you look at their average effect, combine their effect, overall effect. Now that these formulas can be written in some different ways, but mostly, let's say we just talk about the average effect. That will have a Gaussian distribution. Okay. Then there are variants, are the independent events, dependent events. There are conditions, but the central limit theorem is very powerful, and it leads to this thing which I am going to write here, that in notice the original distribution, the underlying original distribution has nothing to do with this here, with the uniformity. Yeah, actually I don't have it here, but I also used to have an example where we started with a continuous random variable that had a distribution looking so strange like this one, Chomsky distribution ऐसी थी, and we started averaging the effects, and this shape started changing into this thing. You can find, yeah. So itni odds, it's a very powerful theorem. Because no matter, in most cases, उसके underlying distribution of each individual random variable could have so many different shapes, so many things, but their combined effect almost always gets here. So it's both the powerful formula one. This is the formula, that is the Gaussian distribution, and we will write it here. Let's say consider a set of random variables. Let's call them x, k. Okay, this is a set of random variables x, k, meaning because I need many of them. Usually I call different random variables x, y, z. Yeah, but now I need so many of them, so I just use a subscript. x1 means random variable 1. x2 means some other random variable. x3 some other. Yeah. So it can be, this is the basic, in its basic form. It can be shown that if all of them have same underlying distribution, so they all come from the same distribution, some fx, like tossing a coin, 4 toss किए, हर toss अकेला किससे आ रहा था, uniform distribution, right? So they were identically distributed, they had the same distribution, yeah, and they are all independent of each other. In our coin tossing example, एक coin toss दूसरे coin toss को कभी इफेक्ट नहीं करती. अगर पहले का मैं बता दूं कि पहले toss का head आया, दूसरे का head या tail. Now we will make this mistake. If I tell you that I toss a coin 1000 times and I got all heads, what's the probability that the next time will be a tail? लोग कहते हैं कि tail की बारी आई हुई है, तो क्योंकि इतनी देर से head आ रहा है. Probability theory says no. वो भी 50% है. Okay, so it can go on head चल सकता है. So all independent. If these two conditions are met, now the power of the central limit theorem is that even if these two conditions are not met and k is large, you still get that bell curve. Okay, but let's say this is called the basic central limit theorem, where we have these two restrictive assumptions. They should come from the same distribution, they should be independent. If these two are met, then this new random variable, let's call it Zn, which represents average effect, so summation xi, I is 1 to n, 1 over n. This special averaging है the overall effect आ रहा है इसका. Yeah. Then the distribution of this guy Zn will always approach in distribution. It will approach the Gaussian distribution as n goes to infinity. In fact, n doesn't have to go to infinity. In most cases, as long as n crosses 32 or there is a number, a rule of thumb. But this जब तीन values तो already curve आना शुरू रहता है, बहुत अच्छा Gaussian का. Yeah. So what you are saying is for any set of random variables that have the same underlying distribution, could be uniform, could be exponential, could be anything else. If they are all independent, then their average will have Gaussian distribution. Now this is called the basic central limit theorem. Basic central limit theorem. The generalized central limit theorem says even if they come from different distributions and even if they are dependent, if the large number is large enough, they will still approach Gaussian distribution. Okay, so that is a generalized one. We don't know. But then what is this then? What is this formula? इसमें किसको approach करना? Shape तो मैंने आपको दिखा दिया. But mathematically then we want to calculate it. Yeah, we won't calculate it here. We will just put that function here. तो वो function है कि जो याद है Gaussian distribution का formula, normal का. Very popular function. That function is so the combined effect has a distribution which is Gaussian distribution, and it has this formula 1 over square root 2 pi sigma e minus x minus mu square divided by 2 sigma square. ये Gaussian distribution का formula है. This formula gives this bell curve. Now you can already see if you are going, this is the mean here, mu center. If you go away from the mean, you are dropping exponentially with the square. ऐसा ही है ना? And it doesn't care if you go away to the left or the right. Equal drop आएगा. So see, equally dropping on both sides. Why am I saying a drop? Because a negative. This value can never be negative because it's square. So the overall has to be negative. So this is always a drop. Variance, this sigma square is always positive value. Yeah. So this is the formula. Sorry, I wrote it for x. So let's just put x. Doesn't matter. It's just a variable. Fx. The Gaussian distribution has this formula. Yeah. And again, whatever you start here, it may have a uniform distribution. These may have like exponential distributions. So they will be 1 over beta e minus beta over x. These with different beta maybe. They will have these functions. But when you sum them and increase their numbers, this whole thing will converge here. Okay, so they will converge to the Gaussian distribution. So it's good to then get familiar with the Gaussian distribution. Yeah. So let's see very quickly. Again, what was the formula? ये आपको आना चाहिए. It's very useful. So we say f x with two parameters mu and sigma square. Yeah, it's 1 over square root 2 pi sigma e minus x minus mu square over 2 sigma square. Okay, and its shape, as I've shown, is like this, the bell curve. And now the mean and variance of this, it has how many parameters? कितने parameters नजर आ रहे हैं? दो है ना? Right? So the Gaussian distribution has two parameters, the mean and the variance. They directly show in the distribution. Many distributions don't have that showing. Like uniform distribution had two parameters, a and b. What was the mean? A plus b divided by 2. Yes? So the mean wasn't showing anywhere in the distribution directly. Yeah, but for Gaussian they show up directly, mu and sigma square. So the mean, as you know, what does the mean do? So if you have a Gaussian distribution with a particular mean, let's say mu1, and another distribution with a higher mean, what will happen? इसकी shape कैसी होगी? Bell shape ही होगा, right? But no, that's with variance. Spread कम है ना? Mean is the central value for Gaussian distribution. वो जो peak है, yeah, for Gaussian. So where is that? If mu2 is higher, so let's say mu2 is here, and what's the distribution? It's here, right? So mean decides where the distribution lies. Location parameter. याद है हमने discuss किया. So as the mu or the mean increases or decreases, the whole distribution moves to the right or left. Now what does the variance decide? Well, the variance decides. Let's clear this. We don't need that. The variance, let's leave it here. If this has a variance sigma 1 square and there is another distribution with a smaller variance sigma, with a larger variance, what will happen?
Cool.
So if it has the same mean, then the center will not change, but the spread will increase. This is sigma 2 square. Remember, variance was what? Degree of spread. So Gaussian distribution is directly showing its mean and variance. So it's very easy to interpret. Yeah, as the mean and variance, if the mean increases or decreases, the whole distribution moves to the right or left. If the variance increases or decreases, if the variance increases, the distribution spreads out. If it decreases, it becomes more concentrated. Okay, and if they're both changing, then you have to combine the effects. Yeah. Now, what other properties does it have? What's the total area under this thing? What should it be? क्या होना चाहिए? 1, because it's a PDF. Yes, you can prove it actually. If you do minus infinity to infinity, put this guy here, dx, you will get 1. Definitely you will get 1. Okay, so this whole area is 1. Now it has another property that the curve is both convex and concave, or concave upward and downward. So look, यहाँ तक, so up to this point, this is concave down. Yeah, from here it becomes concave up. ये जो ऐसे concave का पता ना, concave up. Here also is becoming concave up. इस point को क्या कहते हैं geometry में? यहाँ उसकी direction change होती है concavity की. Point of inflection. Yes, so point of inflection. Now for Gaussian distribution, the center is mu, the mean here, whereas the point of inflection occurs at one standard deviation away from the mean. It occurs at mu minus sigma. Standard deviation is the square root of variance. Yeah, so it occurs at mu minus sigma and mu plus sigma. So that is just some property of it. Sometimes it helps to know that. Of course, we know it asymptotically approaches this thing. So we still have a little bit more time, so I will continue with this. Now, what is the probability? Now, for the Gaussian distribution, like any other distribution, if you wanted, let's say this is the Gaussian distribution. What is the probability that the Gaussian distributed random variable lies between A and B? How will you find that?
So integrate.
Yes, where? Area under this, yeah? This probability x is between A and B is this area. What is the probability that x is less or equal to some value, let's say x1? So you have a Gaussian distributed random variable and you want to find the probability that x is less than x1. This we call the cumulative, remember, capital Fx. वो क्या होगी? Yes, this. And this we call the area under the tail. Usually we have this center and then tails. ये भी लफ्ज़ यूज होता है यार इसके लिए. So this is the area under the tail. So can somebody tell me what's the probability? Let's say if I want to find the area in the other tail. Let's say, or area okay, let's do the simple one first maybe. So you have a Gaussian distribution and I want you to find probability x is greater than x1. Yeah. So what would that be? Definitely this area. Yes. Now we often use that and this together to show that probability x is greater than x1 is actually just 1 minus probability x is less than x1. Yeah, because this is the cumulative distribution function, capital F. So we can use that to get the other distribution. Similarly, there are many other tricks to get the, actually it is metric. So probability that x1 is greater or equal to x is greater or equal to some value here can always be shown that it's the same as less or equal to a similar value. Yeah. So it is metric and it has these values. Now one last thing here that we want to just quickly mention, maybe I'll come back to that in the next lecture also, is something called the standard normal distribution and the concept of a z value. Okay, so we say a normal distribution is standard or it has a standard shape if its mean is 0 and its variance is 1. Okay, so if there is a Gaussian distribution with mean 0 and variance 1, because a Gaussian distribution can have any mean or variance, yes, but if it has these two, we call it the standard normal distribution. So how does the standard normal distribution look? Well, the general normal distribution looks like what? 1 over square root 2 pi sigma e minus x minus mu square over 2 sigma square. Yeah. Yes. So if the mean is 0 and the variance is 1, then it takes the shape or it takes the formula 2 sigma. This is square root of 1 is 1 in this case. So e minus x square over 2. Yeah. It reduces to this shape and this is how it looks. The standard normal distribution, if this is 0 here, its mean is at 0 and its variance, if you calculate it, is 1. That we call the standard normal distribution. Why am I mentioning it? We will do that next time. Briefly, we can cover that and you can see why that is useful. Okay, so any questions about what did we do today? We did the Poisson distribution, yes, discrete case now. Then we went to the continuous case. 3 distributions we covered. Which ones? Uniform, exponential and normal. Yeah, and in covering the normal, we talked about why exactly is the normal distribution so useful or powerful? It's because of the central limit theorem. What is that? That is, whatever micro effects, whatever probability distributions those micro effects follow, if you consider them together, their overall macro effect, that effect in most cases will follow the Gaussian distribution. Okay? Right, so thank you so much, and Wednesday is the mid.